Hi everybody. So today we don't have any video. There's no picture of me, mainly because I have to wear a mask because we have some electricians in the house today. So I thought I'd just keep my camera off. All right. So here is where we ended up last time. So we have we were looking at the quantum harmonic oscillator, of course, and notice here that we were solving for the states, right, the solutions to the TISE, and here's an expression that tells us the states at some n, right, the nth state in terms of the 0th state, and we can get them by applying these raising operators. Okay, so we talked about that last time in your worksheet, was to use the raising operators to get the first excited state, which I've already done for you in a lecture, so that should be easy. And also to use the raising and lowering operators to get the expectation value of x. Okay, using and you can use them to get the expectation value of x because you can write x and p operators in terms of them, like we saw here, and in this example where I calculate the expectation value of p. All right. And now what we're going to do is we're going to look at a quantum mechanical effect that in classical physics doesn't exist. So this is only quantum mechanical. And it's the fact that in quantum mechanics, there is often a probability of finding the particle outside of a classically allowed region. So I'm going to explain what that means. So we're just going to go to a new layer. Here we go. And let me label it. Okay. This is the lecture for 415. Okay. All right. So we are going to, I'm going to put that in my green color up here. So property, I'll put quantum properties, sorry, quantum properties of the quantum harmonic oscillator. And this kind of thing that we're going to be discussing happens for a lot of quantum systems. Okay, so I want to remind you that in our first system that we studied was the infinite square well. So that's the ISW. And in the ISW, remember, our potential energy function looked like this, where this is the 0th level, right? And out here, it was infinity. And out here, the potential energy, again, this is x. This is x equals 0. So this is what I mean by the 0 level, right? This is the potential energy axis, okay? And this is the 0 here, right, for x and a. So this is the width of the well. But over here, the potential energy is infinity. These walls are infinitely high, right? And in this particular case, we said, look, there's no probability at all that you could have the particle be outside in this region here or here. It has to be inside the well. And outside of the well, there's not even any of the wave function. Now, remember, if any of the wave function kind of leaked out, so let's say we had, a wave function that I don't know, looks like this, and somehow was leaking out of the side, right? This is not allowed, right? This is not actually allowed. But if it was, then you know that psi squared, which of course we know is psi star psi, is the probability density of finding the particle outside, right? So if you integrate this, let's say from a to a plus dA, so let's say a, or, well, sorry, from a to, I don't know, a plus some delta, right? So out to here, let's say this is here, delta, okay? If you integrate this psi star psi dx, this would be the probability of finding the particle between A and A plus delta, right? Okay, so notice if I have any wave function out here, any non-zero psi, then I could have a non-zero probability of finding that particle out here. And that, because these walls are infinitely high, that just cannot happen in quantum mechanics or in classical mechanics, either one. So in the infinite square well, you never find the particle outside of the classical region. And in fact, the real wave function has to look like this. It has to go to 0 at the walls, remember that? So whatever it does inside, okay, it does whatever it does inside, but it has to go to 0 at the walls because the wave function has to be continuous and it has to be 0 outside of the walls. Okay, so let's think about, though, what happens in classical mechanics. So now we're going to do classical mechanics, and I'll do that pink, so classical mechanics. Okay, in classical mechanics, let's take a look at a potential energy function. All right, so I'm going to draw some axes in yellow. And here we go. So this is x. This axis is a potential energy, V of x. Okay, and in the classical physics, right, let's say you had a potential energy. Let's make it really simple. Sorry about that. Let's just make it even more simple. Let's have it be, oops, I just want that same color. Let's just have it be something like this. And what I'm trying to draw here, which I'm a terrible drawer, as you all know, is, you know, the 1/2 kx squared parabola that is the potential energy for a spring, a mass on a spring. So you can see the potential energy function is parabolic. Okay. So, and these go off to infinity, as we know, right? Because as x gets bigger and bigger, this thing gets bigger and bigger, is x squared. And in classical physics, if we start a particle off with a particular energy, so let's say we started a particle off here, and I'm going to make the particle a different color, or blue color here. So let's say we have the particle, let's start them off with at a particular place, okay? So this is equivalent to taking, you know, our mass on a spring. So we have a mass on a spring. And, sorry, this is supposed to be the ground. There we go, that it's sitting on. I can't draw that. Apparently cannot do that. Okay, so we would pull it out. So here's the equilibrium position, right, at x equals 0. This is here. X equals 0 is right here. Okay. And you pull the mass out to some other place out here and then let it go, right? So here's the mass. You pulled it out to some location here, and that's going to be the amplitude. Okay, so let's say that that point is right here. Here's A. And you pull the mass out. Now, right at A, if we go up here, here is the energy, the potential energy that I'm going to have when I pull the mass out to here, right? Now, I haven't let it go yet. As soon as I let it go, right, it's going to have kinetic energy. It's going to start building up kinetic energy, right, until it gets to here where it's the fastest and the potential energy is 0. So if we look at the trajectory, it's going to go, at this point, when I pulled it out at A, let's be clear, the total energy is equal to 1/2 k A squared, right, because x is equal to A out here. This total energy is never going to change. We're not going to have any, we're having no friction or anything. Just like in the quantum harmonic oscillator, there's no friction. So this energy we can represent by this, like a straight line across, like this. Okay? All right. So now as the particle starts to go back towards x equals 0, right, it's going to start off with all potential energy, and then it's gaining the kinetic energy. Remember, kinetic energy is the difference between these two things, right? Difference between total energy and potential energy, because remember, the total energy is the potential energy plus the kinetic energy. All right? So the kinetic energy, so this is the KE, right? So this is v of x here. So the Ke is equal to E minus v of x. And that's this little blue line here, right? So the blue distance here, E minus v of x. E minus v, okay? So as it heads back to the middle, it's gaining more and more kinetic energy until it gets its maximum here. This is the maximum kinetic energy when the potential energy is 0, right? And then, of course, as you know, it's going to come past that equilibrium point and slow down again, right, till it stops here and turns around. Now, in fact, these 2 points here, this one and this one, these are both called turning points. Okay, this is where the particle is turning around, right? And going back and forth forever, right? Because there's no friction. All right, now, here's the key. In classical physics, there is no way for this particle to go outside of this region. So here we are at A. Over here now is going to be, of course, as you probably already can guess, minus A, right? So if this is, you know, I don't know, 10 centimeters A, it's going to go up to minus 10 centimeters away from the equilibrium point, and it's going to go back and forth and back and forth, okay? Now, there's just no chance for it to go past A, right? So let's say it's gone over here, it turns around, it comes back. It's never going to go past A, right? Because if it could be out here, let's say if it was here, right? At this point, what is happening? Well, notice that at this point, the potential energy is way up here, right? Higher than the total energy, which is represented by this level, this line. Okay, so that's not possible. It can't be outside these regions, okay? It can't be outside the turning point. So wherever you started off, you could start it off over here, this A. It's going to go back and forth like this and never pass that pink line. Okay, keep that in mind. That's how classical physics works. Okay, so the point here is just in classical mechanics, you can't cross your turning points, right? Because your energy would now be, your potential energy in this case would be higher than your total energy, and that's not allowed, right? Okay, so keep that in mind. So what we are going to do is we're going to try to show, right, to calculate for the quantum harmonic oscillator, we're going to calculate probability of being outside of the classical turning points for a given energy. So for a given energy here, right, I pulled it out to A, the total energy is here, right, in this blue line, and the turning points are here and here, right? So we would like to calculate what is the probability of finding the particle outside of the classical turning points. Okay, now we know in classical physics that probability is 0. Okay, and we're actually going to first calculate the classical probability. Okay, all right, so, and that's going to help us with the quantum mechanical probability as well. So let's get started. Let's go back to green. So we're going to calculate the probability of the particle being outside of the classical turning points. Okay, so in a region in which it's really not allowed in classical physics. Okay, so let's just think classically though, right now. We're going to just we're going to think as if we're calculating this for a classical particle. And think about the fact that in a harmonic oscillator, right? So just think classically now. We know the particle's going back and forth, right? Like the mass on the spring, back and forth and back and forth. And we think about it traversing this area between minus A and A, right? So it's going back and forth. It's kind of traversing this this region between minus a and a, right? Between x equal minus a and x equal a. All right. So what is the time that it would take for it to go back and forth, right? One traversal, so that means just going, let's say, from minus a to a, or from a to minus a, that's half a period, right? So the time to go half a period, so let's call the period tau. I'm going to use blue because we're going to stay in our classical. So tau is equal to the period. And remember, period is defined as, say, starting at a, like we started it off, going to minus a and coming back to a. That's one period, right? That's how long that takes is one period. Okay, so the time for one traversal of this area of this area between minus a and a, is going to be tau over 2, right? Okay, and the amount of time the particle spends in some small region delta x, so say we have a small region here, dx, right? And we want to know how much time does it spend there? Well, that's pretty easy because I can just say, look, that's going to be, how much time does it spend there? Well, it's dt over dx times the velocity, right? Right? And so that's just, that's pretty simple to understand because, right, x equal vt, right? And where its velocity does change with x, as we know, right? Because it's going fastest here in the middle and slowest here at the points where it stops, right? The turning points. Okay, so the probability of finding the particle in some small region is basically the time it spends in that region over the total time it takes to traverse this whole region, right? So part over the whole. Okay, so let's say that probability. So the probability of finding particle in the small region dx, or some small region, I should say some, not the, some small region dx is just going to be how long it takes to traverse that small region dt over the total time of traversal, one traversal, right? Tau over 2. Okay. So the classical probability as a function of x dx, so that's the probability density, right? Because it's okay, because the probability is all of this together. As we know, it just definition-wise, this is probability of finding particle between x and x plus dx. Okay, I remember that. Is just this. So let me write it again. P classical is just dt over tau over 2. And I can replace that now because dt is this dx over v, right? I'm going to pull the 2 up as well, just so it's not annoying me. So let's see, 2 over tau, and then dx over v of x. Now be careful, this is the velocity, not the potential energy function. So here we should put little bars on our v to make sure that it is definitely not the velocity, and let's not get confused, okay? That's the velocity, this is the potential energy function. Okay, so this is the velocity. So this should make some sense because the probability of finding it between x and x plus dx will change depending on how fast the particle goes. If the particle is going super slow, right, so v is really small, the probability is going to go up, right? It's easier to find it. What's the higher probability of finding it in a region where it's going slowly, right? Okay. All right. Now, is this normalized? And we should always ask that question when we have a probability distribution. Well, let's look. So let's call this well. how about this? We're going to go, we're going to normalize. So we're going to go from minus A to A. And P classical of x dx, okay? And because I'm actually going to integrate this over time, it's a little easier. So I could put all this in, but it's easier because I don't want to have to put in, I really have an expression right now for the v of x. I'm going to actually change that in a little bit, but right now I don't. So I'm going to use the time version of this. So here I'm going to change this to tau, so ta, t minus a, to ta. So in other words, the time where it's at minus a to the time where it's at a, dt over tau over 2. And that's easy to integrate. So I'm just going to have, this is just going to be 2 over tau, and then I'm going to have t at minus a minus t at a equals, and this, as you notice, if ta minus t of minus a minus t of a, that's 1/2 a period. So this is actually tau over 2, and these things all, this will cancel, 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 and you get 1. So indeed, it is normalized. And in fact, you're going to find very often that if you have a classical probability, right, it's kind of built to be normalized already, and usually is, but always check. Okay. All right, so now let's, like I said before, we can write the velocity, right, in terms of our total energy. So let's look back up here, right? So let's solve for v in terms of, and I'm not going to use this version, I'm just going to use capital V. Sorry, I should put that's a capital V. So I'm going to say this is E minus V, that's the KE, right? So remember that's 1/2 mv squared, okay? And now I'm going to solve for v because I need it here. All right, so let's see. So what do I get? I get v of x, and I should put my little, yeah, I should, let me erase that because it really looks like my other v and it's annoying me. So v of x, okay, is going to be equal to, let's see, we're gonna multiply by 2, we're gonna divide by m, and we're gonna take the square root. Okay, so we get 2 times E minus the potential energy function over m, all under the square root. Okay, so that's great. So I'm going to put that in here. So here, my P classical now, and we already know it's normalized, is 2 over tau, and then dx over v, which is the square root of 2 times E minus, sorry about the banging, that's the electricians, the potential energy function over m. M is in the square root. Sorry, it's not clear, but m is in the square root. Okay, and I'm just going to mush this around a little bit to make it a little better. Okay. So here, need a second just to read my notes. Yep, okay. So let's write 2 over tau, and then dx, and then the square root of, I'm bringing the m up at the top because it's annoying to be at the bottom, over 2 times E minus the, remember, potential energy function. Okay, there we go. So the classical probability here is just this guy, right? The probability density. If we look, right, what happens when E minus V, right, we saw this before, when E minus V is very small, right, so when E minus V approaches 0, that's where we're getting to the turning point, right? Because E minus V is this difference here, these bar differences, right, this distance between the total energy and the potential energy, okay? So as we get really, really close to the turning points, this thing blows up, right? This probability blows up. So if I were going to draw this probability on this graph here, right, and I'm going to do that in a different color, maybe the orange color, I would sort of draw these minus A and A as these asymptotes, because as the either side there, right, when the particle's approaching either minus A or A, this thing is blowing up because it's this whole term here is going to make this whole probability blow up. So basically, the classical probability density looks like this, right? So it's kind of like this function that's going to asymptote to these lines. So let me draw that in a little better. It's going to asymptote to those places where the turning points are, right? To the minus A and A. So it's going to infinity, right? But you can see that there's no place that probability is going to be outside of the turning points, right? There's no way. Okay, now we're going to do some changes of variables here to try to get it into a form where we can, well, I think we're probably going to be okay with the form we have. So let's see. Let me just check this for a second. Okay, so now we need to just change some of our variables. So for instance, we have tau, the period, right? And if you remember that tau is equal to, oops, I need my blue color back. Sorry. Tau is equal to, let's get rid of that, sorry, 2 pi over, whoops, that's supposed to be a pi. That's not good. 2 pi over omega. Remember, omega is the angular frequency, right? So this is the period, is 2 pi, so it's 2 pi over omega. Remember, omega is in hertz. So this would be 1 over seconds, right? Omega is in radians per second, and so the second would come up here, and the radians would cancel out, and you just get seconds. Okay, and remember that in the quantum harmonic oscillator, right, we had V of x was, you remember V of x is 1/2 kx squared, but that k is equal to, sorry, that's weird, my pen went crazy. K is, sorry, remember that omega, sorry, is the square root of k over m, right? All right, so we can write omega squared is k over m, and k is m omega squared. And we already did this before when we set up the oscillator. So 1/2 m omega squared x squared, okay? That's what we had for when we solved the TISE. Okay, great. So here we can see that omega is square root of k over m here. So tau is going to be 2 pi over the square root of k over m. Okay, but k is, well, I'm sorry, we should have just left that in terms of omega. That was dumb. Let's leave it in terms of omega. That would be a lot easier. All right. Okay, so we're going to be substituting some of this stuff in, right? So for instance, here's tau. So I'm going to put that in here, and I have 2 over 2 pi, and that's over omega, so the omega comes up here. And then we have the square root of m, and then over 2e minus the potential energy function v of x. Okay. All right. So now I have, let's see here. Yep, I can sort of break some of this in. So the 2's are going to cancel, and we're going to end up with our final expression that we're going to use. I'm going to bring the omega squared in, the omega in, sorry. So I'm going to have square root of m omega squared over 2e minus the potential energy function And there we go. Okay. And that's all. I forgot my dx over here. Dx. Oops. Dx. Okay, so that is the expression that we have, and I'd like to turn this into a quantum mechanical expression. I'm going to get another layer. So let's get another layer, and I'll label it. You can either pause the video to catch up, or I'll give you a little time while I label my layer. Whoops. All right. And turning off this layer. Okay. All right. So now I'd like to make a connection with our quantum harmonic oscillator. So I'm going to write down what we have again, right? So we have the classical, P classical. I'm going to leave the dx off. So P classical is the square root, or so 1 over pi times the square root of m omega squared over 2e minus the potential energy function. Right? Okay, so that's what we got so far here. So that's the classical probability. Okay, so remember we have our classical probability here. And notice that if we wanted to find the probability of the particle being outside of the classical regions, minus a and a, technically we would integrate this from a to infinity, so this whole region outside, right? But we can't even really do that for the classical probability, right? Because if you look, right, in this region, E is smaller than V, right? Here's V, here's E. So as soon as you move past A, E is smaller than V, and you're going to get a negative under the square root, and the whole thing's undefined. So you can't even actually do that integral because it doesn't make any sense to do that integral. The probability is clearly 0 for the particle be out here or out here. Well, what about for quantum mechanics? Okay, so how do we calculate the probability in quantum mechanics? Well, for quantum mechanics, right, we, of course, calculate this integral, and let's say between a and infinity, right? So that's this region here that I've shaded all the way out to infinity of psi star psi, right? So psi star psi dx. This is the quantum mechanical probability. So let's actually do this and see what happens. Okay, so what I'm going to do is I'm going to pick a particular psi for the quantum harmonic oscillator. I'm going to pick psi 0. And we know psi 0 is, let's see, the square root, sorry, it's not square root, it's m omega over pi h bar to the 1/4. E to the minus m omega, I always forget, m omega over h bar, 2h bar, sorry, 2h bar. Okay, so, and there's an x squared up here, sorry, the x squared, there we go, that's the psi naught. And of course, E naught, I wrote the energies up here, for n equals 0, sorry, is h bar omega over 2, right? Because if we just put n equals 0 in here. Okay, so, so here we can actually calculate that. So now we're going to calculate the integral a to infinity of psi 0 star psi 0 dx. And we're going to substitute everything in here. And this is going to be m omega over pi h bar to the 1/2. and then e to the minus m omega over h bar, right? The 2 goes away because there's 2 factors of the e to the x squared stuff here. To the x squared dx, okay? And now we're going to make a substitution to take care of all these constants. All right, so we're going to do the substitution where this little thing called c is the square root of m omega over h bar x. And then dc would be the square root of m omega over h bar dx. Let's think about A, right? So one thing, A is the amplitude. So remember that the total energy, E n, is related to the classical 1/2 Ka squared, right? This is the classical version of the energy, of the total energy of an oscillator. And remember, the K is m omega squared, right? And so this is going to be m omega squared a squared. And the En we have here for E0. So we can call this A0. Let's call it A0. So we have 1/2 m omega squared A0. This is going to be the turning point for the 0th energy. Because notice if I put energy at the different places on this, if I draw this total energy line at different places on this graph, I will have different values of A. So A0, right, is equal to E0, which is this h bar omega over 2. So A0, oops, sorry, squared. A0 is, let's see, the square root of, and then we have h bar omega over 2. Then we have a 2 on the top from here, and an m omega squared on the bottom here. And that all comes out to, cancels out the 2, cancel out this, h bar over m omega. So that's A0. And notice that if we put that value in, so what is C at x equal A0? Well, let's see. So it's the square root of m omega over h bar, and then it's the square root of h over m omega. That's A0, right? That's at x equal A0. And you just get 1. Okay, so here when we do our u substitutions, right? So first of all, we have our m omega over pi h bar to the 1/2. Here, I just pulled it out. And then dx is, you pull this up here, right? So dx is equal to the square root of h bar over m omega dc, right? So we're going to put that in here, right? So we have the square root of h bar over m omega, and then we have the integral from A0, right? A0. I put the A0 there. I should have put that on there. There we go. A0. So A0 for C is 1 to infinity. And then E, so notice here that m omega over h bar is times x squared is c squared. So minus c squared dc. Okay, great. Now notice this is going to cancel. And we're just left with 1 over the square root of pi. Then integral 1 to infinity e to the minus c squared dc. Now, think about it for a second. This is the probability that you find the particle in this classically disallowed region. But I'd like to know the probability of finding it in both of the classically disallowed regions, which is here and here. But because this is symmetric, right, this should just be 2 times that. So the total probability of finding particle in classically disallowed regions is equal to 2 times this integral. Okay, so now we're ready. Now, this integral is a very interesting integral. It does not have what we call a closed form. It is evaluated numerically, and it is called the associated, I think it's associated or complementary error function. So it's called, it has this form, ERF of C. So if you look up ERF C of C, you'll find an integral looks exactly like this, except for here. Oh, I'm sorry, that is absolutely not correct. It's not of C. It's of B. Okay, and it's actually this integral when b equals 1. So in other words, their ERF-C function looks like this. It's defined as an integral 2 over the square root of pi, so it actually has the 2 over the square root of pi, and then whatever this limit is the b, and then infinity is always the top limit, and then it's e to the minus c squared dc. Okay, so this, if you go look it up, it'll say ERF-C of x, but I put in b here because I don't want to confuse anybody with x, okay? But it's just, this is a numerical value, so whatever this is, you can now go look up a table, or there are integrators on the internet where you can just stick in whatever value and it'll spit out what this is supposed to be. And let's see, I have the table here. Here it is, ERF-C. And what you can do is you can go look at x. So in other words, the x here is b. Okay, and there's the error function and then the ERF-C function, right? And if we look, right, we know that ours is 1, right? So our b is 1. Okay, so we'll go look to 1 right here, and ERF-C function is 0.1572992. Okay, so our probability is 0.157. I'm not going to get any more decimal places back that, right? So there's a 15% chance, or 16 roughly percent chance of finding the particle outside of the classically allowed regions. Okay, so this is unique to quantum mechanics, and the wave function actually, and I'm going to show you a simulation in a second that shows you the wave function for the quantum harmonic oscillator. Does have, right? It does have some of the wave function sort of leaking out of this classical region, and it must, because this probability is non-zero, right? So here we go, 15.7% chance of, oh, why did I put change? Who knows? Okay. Chance of finding particle outside a classically allowed region. Okay, kind of amazing. All right, so I'm going to show you that simulation now. Okay, so this is the quantum bound states FET that you can get at the University of Colorado website. Just Google bound state or quantum bound states PHET and you'll find it. So we're going to set this for the quantum harmonic oscillator. There we go. So this is our potential energy function, and these are all the energy levels, right? Here's the ground state energy, etc. Okay, now I want you to take a look at the positions -1 and 1. And I'm going to pick an energy here that has turning points at -1 and 1. So right here. Okay, now look at the wave, this is psi star psi, right? Look at the wave function. And you can see that it has some weight outside of the classical region, right? And we just proved that even the ground state does, right? So in other words, if we go here, the turning points are in here. It's harder to see because that's a line like right here. It's just hard to draw that line on this. But you can see that there's weight, and we just proved there's a 15% chance of finding the particle outside of the main region. Okay, so your homework for this lecture is going to be basically going through the calculations that we just went through, okay, with a little extra. So I want to see all of your work since I basically went through it for you. All right, but I want you to understand all the steps that we took. All right,